Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. This week, we have a very special interview for you. Those of you who've been receiving my newsletter for a while might remember that while in Switzerland last month, I had the pleasure of interviewing Jurgen Schmidhuber in his lab at IDSIA, which is the Dalle Molle Institute for Artificial Intelligence in Lugano, Switzerland, where he serves as scientific director. In addition to his role at IDSIA, Jurgen is co-founder and chief scientist at NNaisense, a company that's using AI to build large-scale neural network solutions for superhuman perception and intelligent automation. This is absolutely the furthest I've ever traveled for an interview, but I was in the neighborhood, so to speak, and boy, was it worth it. Jürgen is an interesting, accomplished, and in some circles controversial figure in the AI community, and we covered a ton of really interesting ground in our discussion. So much so that I couldn't truly unpack it all until I had a chance to sit with it after the fact. We talked a bunch about his work on neural networks, especially LSTMs, or long short-term memory networks, which are a key innovation behind many of the advances we've seen in deep learning and its application over the past few years. Along the way, Jürgen walks us through a deep learning history lesson that spans 50 plus years. It was like walking back in time with the three-eyed raven. I know you're really going to enjoy this one. And by the way, this is definitely a Nerd Alert show. A few key announcements before we jump into the show though. First off, I want to give a big thank you to our friends at Cloudera for sponsoring this episode. You probably think of Cloudera primarily as the Hadoop company, and you're not wrong for that, but did you know they also offer software for data science and deep learning? They do. The idea is pretty simple. If you work for a large enterprise, you probably already have Hadoop in place, and your Hadoop cluster is filled with lots of data that you want to use in building your models. But you still need to easily access that data, process it using the latest open source tools, and harness bursts of compute power to train your models. This is where Cloudera's Data Science Workbench comes in. With Data Science Workbench, Cloudera can help you get up and running with deep learning without massive new investments, by implementing an on-demand self-service deep learning platform right on your existing CDH clusters. From a tech perspective, DSW is pretty cool. It uses Kubernetes to transparently scale workloads across the cluster, supporting R, Python, and Scala, and deep learning frameworks like TensorFlow, Keras, Caffe, and Theano. And as of last month's 1.1 release, GPUs on the Hadoop cluster are fully supported. The folks at Cloudera are so confident that you're going to like what you see that for a limited time, they're offering a drone to qualified participants simply for meeting with their sales representative for a demonstration of the Data Science Workbench. For your demo and drone, visit twimlai.com/Cloudera. That's CLOUDERA. Next up, a reminder to register for our online meetup. If you missed the first meetup, we expect to have the recording online later today. You'll be able to view it at twimlai.com/meetup, which is also where you can register for the next one, which will be held on Wednesday, September 13th. We're currently finalizing the topic, but if you're registered, we'll notify you as soon as that's done. Finally, if you like the podcast, please go ahead and sign up for our newsletter, which is the best way to keep up to date with me and what's going on the show, my picks and thoughts for what's new and important in machine learning and AI for the week, and exclusive promos and giveaways just for newsletter readers. To subscribe, visit twimlai.com/newsletter. And now, on to the show. All right, everyone. I have the distinct pleasure of being here with Jurgen Schmidhuber, who is the scientific director of the Swiss AI lab, IDSIA, as well as a professor of artificial intelligence with USI, the University of Lugano, and SUPSI, the University of Applied Science and Art of Southern Switzerland. as well as being the chief scientist for NNaisense, a company that he co-founded. Jurgen has a long history in artificial intelligence and is widely recognized as being a pioneer in the development of recurrent neural networks and in particular LSTM neural networks, which we've talked about quite a bit on this podcast. Super excited to be here with you, Jurgen. Welcome to This Week in Machine Learning and AI.
It's my pleasure, Sam.
So I like to get these conversations started by just having you introduce yourself and tell us a little bit about how you found your way into the field of artificial intelligence.
I can do that. When I was a boy, I tried to figure out how can I maximize my impact, and then quickly it became clear to me that I have to build something that learns to become smarter than myself, such that I can retire, and such that this smarter thing is going to further self-improve and solve all the problems that I cannot solve. And that's what I've been trying to do for the past 3 decades or so.
So you've got a lot going on. I mentioned a bit of it in the intro. Tell us a little bit about how you spend your time and some of the research efforts that keep you occupied.
In many ways, I'm still doing the same thing that I've started to publish on in 1987, which is build this general purpose learning machine, which learns to better and better understand the world and learns to exploit that knowledge about the world to become a better and better and more general problem solver. And over the years and decades, we have made a couple of insights related to fundamental building blocks that you need to build this full AGI system, but we are not yet done. And some of the puzzle pieces still have to fall in place in a way that we are trying to push both at the Institute for Artificial Intelligence, at the Swiss AI lab IDSIA here, and in my company NNaisense, where the goal is really to build a general purpose AI that learns to do not only one thing in a particular domain, but then learns on top of that to learn a new profession in another domain, and then on top of that, yet another thing, such that it becomes a more and more general problem solver and even learns the learning algorithm itself, such that it's not always stuck with the same initial learning algorithm, but learns to improve that method itself, such that it learns to improve the way it improves itself, and so on. And you can imagine that on the way to that goal, there are all kinds of little sub-problems coming up, and we always focus on the most promising ones. Sometimes you don't have to build a full AGI to solve interesting problems. Sometimes just better pattern recognition will do the job in certain applications. And so pattern recognition, which is a tiny part of the full AI thing, that is something that has become really commercial in recent years. Some of the techniques that we have developed in the past decades are now really useful in commercial applications, such as speech recognition and machine translation and all kinds of pattern recognition. So what is the daily procedure? There is no recipe for that. You try to make progress here and there and there, and sometimes you seem to be in a dead end. In fact, most of the time you are in a dead end, but then you backtrack, and after 100 dead ends, there's again some sort of progress, and that's worth it, because from there then new search paths are opening up and new dead ends, but also new progress is coming in.
I get the impression that a lot of contemporary machine learning and AI researchers are not driving towards a vision of AGI. They're solving specific point problems. Do you feel that pursuing your research in the context of trying to create a generalized AGI gives you a different perspective, or heads you down a different path, or gives you a different approach?
The goal of AGI certainly made a difference to us. First of all, if you want to build a general purpose learning machine, then you need a general purpose computational architecture. And in our field of neural networks, that means a recurrent neural network with feedback connections, which is much more powerful than what most of my colleagues have been studying most of the time, which are so-called feed-forward neural networks, which don't have feedback connections. The difference between a recurrent network and a feed-forward network is a bit like the difference between a general-purpose computer and a mere calculator, because on a general-purpose recurrent network, you can run arbitrary sequential parallel programs, as opposed to a feed-forward network where you just can shift information from an input to the next layer and then the next, and finally you have a result that is determined through a very limited feed-forward computation, where many things that you know from traditional computer science are not possible. So, to build a general AGI with neural networks, you have to start with recurrent neural networks. And the work that we have been doing in the past decades really has focused on that. In the late 80s, I started to work on these recurrent networks, which are more challenging than the feed-forward networks, because you have to deal with the space of all possible programs that you can implement on a general-purpose computer. So basically, you have to search in the space of all programs to find solutions to problems. This makes it hard, and soon we ran into problems with that approach, and the traditional recurrent networks didn't really work well, and so we had to come up with a couple of improvements such that you can really use and exploit this power, the theoretical power of recurrent neural networks.
Before we dive into that, I'd like to further explore this notion of a RNN as a general computer, as general compute framework. I think that's not obvious to a lot of people. And as an example, I don't know if you've ever heard of this FizzBuzz with TensorFlow. Does that mean anything to you?
TensorFlow means something, but FizzBuzz doesn't. What is that?
FizzBuzz is a common programmer interview question, and it's you tell the candidate to write a program that basically, I forget the specifics, but it's something like prints fizz when it runs through a loop of numbers and prints fizz when the number is divisible by 3, and buzz when the number is divisible by 5, and fizz buzz when the number is divisible by 15. And so it's, if you know how to do a loop and use mod, right, it's very easy to do. Yeah. And someone with some experience in deep learning and TensorFlow got asked this question on an interview, and they decided it inspired them to try to figure out how they would accomplish this with deep learning. And in fact, I think the result of their experimentation was that this thing that's extremely, extremely simple to do with common, general purpose programming is very, very difficult to do with neural networks. You have to come up with a lot of data. You have to train these networks, and they still, because it's probabilistic, they still get it wrong. And so with that as context, I'd love to hear you kind of further explore this idea of RNNs as a general purpose, computer.
Yes. Now, first of all, how do you see that an RNN, a recurrent neural network, is a general purpose computer, as general as your laptop? Well, you can take some parts of the recurrent network and wire them up as NAND gates. Not AND gates, NAND gates. Very simple, very tiny little subnetworks. And then you just have to recall that that's
what your computer is.
The CPU of your phone or of your laptop can be emulated by a network of NAND gates. It essentially is a network of NAND gates, which means you can essentially emulate your laptop and whatever program is running on it on a recurrent network. In a certain sense, your microchip in your phone is just a very sparsely connected recurrent network. So that's step number one. Let me give you an even simpler example where you see how elegant and powerful recurrent networks can be in comparison to feed-forward networks. Let's look at the problem of parity. Suppose somebody gives you n bits of information, 10, 11110, and you should classify that as to whether the number of ones in that sequence is even or odd. So that's the parity problem. Now you can indeed wire up a feed-forward network which has, say, 10 different input units to implement this mapping, which maps the input string to a decision, either this is an odd number of ones or an even number of ones. And it will take you a rather big network with lots of connections. And it will never generalize to 11 bits or 12 or something, because the input size is so limited. Now, with a recurrent network, you can solve the parity problem much more elegantly. You just feed in the bits one by one into a recurrent network that just has one input unit and one internal hidden unit and one output unit and maybe an additional bias input unit if you know what that is. And then you have just 5 connections in this little network, and you feed in the input string 10, 111, one by one, and all the network has to learn to become a flip-flop, because whenever a new one is appearing, then the internal unit that represents what the network has seen so far just has to flip its state. And that determines then, is the current number of ones, is it odd or even? Right. So this program for the recurrent network is so simple. It fits into 5 connections, and you can easily guess those connections. You just do 1,000 random guesses for the 5 weights, something between -10 and +10, and you test the result on a tiny little validation set, maybe 3 patterns, 3 different parity problems. And if it works on that, you can be almost sure that it's going to generalize to all possible parity problems, not only those where there are 10 bits coming in, but also those where there are 5 bits coming in, but also those where there are 5,000 bits coming in. So the natural and elegant sequential solution to the parity problem easily fits into a simple recurrent network, and it needs a really awkward, complicated feed-forward network to solve a tiny part of that for just exactly 10 bits, say, or 15 bits. Sure. So this is to illustrate that the difference between a recurrent neural network and a feed-forward network is like the difference between a general purpose computational architecture and a mere calculator.
Is that to say then that referring to RNNs as a general purpose computing system is way more general purpose than feed forward, but we still have a ways to go in our ability to train these things in order for them to be truly as general as our current computing architectures? Maybe another way to ask that question is, like, what's the fly in the ointment here? What are the limitations in the way we deal with these with RNNs that prevent us from using them as general purpose computing system, as you kind of assert?
Yeah. So it's one thing to have a general purpose computing architecture, and it's another thing to learn the programs running on that architecture, which are solving your favorite programs.
Right. To put that into an example, so we know that these RNNs are basically functions to transform inputs and outputs. And so there's some set of inputs that produces the output of your arbitrary software program, whether that's, Mac OS or what have you. But learning that function based on the inputs is a whole different story.
It's a whole different story. The learning of the programs running on your general purpose devices, on your recurrent neural networks, that is the really interesting part. And people have tried it for a long time, but only with certain tweaks to the original concept of recurrent networks, it became feasible in practice, and it became so powerful that it's now all over the place in every smartphone.
So we're going to talk about that in 1 second, but I'd like you to provide a little bit of historical context for RNNs. You started working on these at a time when feed-forward networks were considered the state of the art, and you've seen the way you've seen the evolution of RNNs. Tell us a little bit about that history.
Mm-hmm. So maybe let's start with the history of deep feed-forward networks, which go back to 1965. When I was a baby, I was 2 years old back then. And there was this famous mathematician, Ivaknenko, in the Ukraine. And with his student Lapa, they published this method for training deep feed-forward networks. They didn't even call them neural networks. They called it the group method of data handling. But that's what this stuff was. It was deep multi-layer perceptrons, and they found a way of learning internal representations in these deep multi-layer perceptrons. And by 1970, they already had networks with 7, 8 layers, and many people built on that later.
And so, deep in there at that time was on the order of 10?
On the order of 10, yes. And even by the standards of the new millennium, this was deep. Right. Because most people in the early 2000s didn't use networks that were as deep as those of Ivaknenko.
True.
And he did that in 1965.
Right.
That was 4 years before Minsky and Papert wrote a book about the limitations of shallow networks with one single layer, which is called Perceptron, and which is sometimes credited for killing neural network research in America, because people thought, oh, if these guys are so limited, then we shouldn't further progress there. We shouldn't further work on that. And maybe it was a Cold War thing. Over there, on the other side of the Iron Curtain, back then this was the Soviet Union, It wasn't the Ukraine, it was the Soviet Union. And there were these people who had already deep learning networks back then. However, then in the 80s, the more general attempts came where you really try to work with recurrent networks, with general purpose computers, not just feed-forward networks. And you want to have these recurrent networks for all kinds of interesting applications, such as, for example, speech recognition or video recognition, everything where there are sequences. For example, in a video, you don't just have one single image, which you want to classify. No, you have a whole stream of images. And every few milliseconds, a new image is coming in, which means your network somehow has to memorize what it saw before in order to make sense of the current input within the temporal context of before. So it has to learn to memorize the important stuff and to ignore the unimportant noise. And this proved to be very challenging. And people then already in the 80s realized that the first attempts at recurrent networks didn't really work well.
And what specifically didn't work well about them?
They especially failed when there were long time lags between relevant input events. For example, in speech recognition, suppose somebody says 11 and another guy says 7. And then the end of that is always even. So to see the difference, you have to memorize that he say s or 50 time steps ago, because even by itself already consumes 50 time steps, more or less, because roughly every 10 milliseconds, a new input vector is coming from the microphone. So you have to look back 50 steps. Right. And in many other applications, for example, as you are listening to me now, to make sense of what I'm saying, you have to look much further back in time. You have to think back of the beginning of our discussion to make sense of what I'm saying now. Right. So thousands and hundreds of thousands and millions and maybe billions of steps you have to look back to take into account the temporal context. And it turned out that these original networks of the 80s, they could look back only for 5 steps, 6, 7, something like that. So it was completely insufficient for doing interesting things.
And this is a problem that came to be called the vanishing gradient problem, among other.
And then we tried to figure out what is the reason for that. And my first student in 1991 was Sepp Hochreiter, my first student ever. And his task was to figure out what is the problem.
And were you here at the time? Or?
And we were back then not in Switzerland, we were in Munich.
Okay.
This was done in Munich, at the Tech University of Munich, TU München. And Sepp, in his thesis, in his diploma thesis, showed that the problem is that these error signals that you are getting through backpropagation in these recurrent neural networks, as you are propagating them backwards from the output layer towards the previous layer and then the layer before the previous layer and so on, they get smaller and smaller in a way that is catastrophic in the sense that the shrinking happens in an exponential fashion. So as these signals, which tell the system how to change its connections in order to become a better system, as these signals are being propagated back into time, so to speak, they are getting smaller and smaller in an exponential way, or they explode in an exponential way. So either the gradients, for those who know what that is, they explode or they vanish. And in both cases, these traditional recurrent networks cannot learn anything. At least they cannot learn to look further back in time than, say, just a few time steps.
Right. So just to try to paraphrase that to make sure that I'm understanding. So the way we solve these deep neural networks is to use backpropagation, basically, to start with the output and work our way back to the input layers. And we do that using gradients, which essentially, let's say modulate the error that is propagated out to the output. But if you go back far enough in your network, or if your network is too deep, then you're not getting enough signal back towards the beginning of your network to make the necessary corrections to improve.
Yes.
Is that basically what you found?
Yes. Let's maybe quickly step back a few decades. In 1970, there was this Finnish guy, Seppo Linnainmaa, in Helsinki, and he described for the first time the modern version of what is now called backpropagation, which is a method for adjusting a deep network of nodes, of computational nodes, such that you can figure out for each of these nodes and for each of these connections, how much did this connection contribute to the error that you observe at the output of the network. Mm-hmm. So at the output of the network is computing some result which is different from what it should have computed. And the difference is called the error. And now you want to figure out for each connection in your system, how much did this particular connection contribute to this error out there? And you want to change then the connection such that the total error gets smaller. And Seppo Linnainmaa, this guy in Finland who was a master student back then, he wrote down this technique of automatic differentiation, or today it's called backpropagation. Mm. And then people started using that in the 80s for training neural networks. Okay. And then also generalized it to the case of recurrent neural networks, where you have feedback connections and where you still have the same basic approach. As you are trying to compute for each connection in the system, how much did it contribute to the error at the output side at some later point in time, you are moving backwards from the output layer towards the time step before the computation of what you find in the output layer. And then there are certain things which are called error signals are being propagated back. And then from there, they go one step further back, and then from there one step further back, and so on, until they basically traverse the entire network in a way that allows you to compute for each connection in the system how much was it responsible for the final error. And then through the work of Sepp Hochreiter, my first student in 1991 in his diploma thesis, it became clear that the gradients are vanishing. These error signals that are being propagated back, they are quickly vanishing, which means that although the whole idea is nice in principle, it doesn't work in practice because very quickly you don't have any signal any longer, which allows you to improve your network such that it becomes a better network.
Right. Where or when did gradient descent come into play in all this as a method for solving these types of networks?
Seppo Linnainmaa in 1970 formulated it as a very general method for all kinds of networks. consisting of differentiable nodes.
In that paper where he talks about backpropagation, was he also applying gradient descent, and did he introduce that then?
Yeah.
As the method
so
for...
gradient descent is a much older technique, which goes back at least to Hadamard around 1900 or something like that.
Mm-hmm.
So gradient descent is a very old technique.
Right.
And then the main question is, how do you efficiently compute gradients in complex systems, such as these complex networks, where one node is computing something that depends on the activations of other nodes, and then is broadcasting its own result to all kinds of other computational nodes, which again compute something new based on these broadcasts from all the other nodes, and then send their results even further, and so on. So once you have a very complex system like that, then how do you do the credit assignment? How do you figure out how much should you change this connection there, which was active maybe 100 time steps ago, which nevertheless had an impact on what happened 100 time steps later at the output side?
Mm-hmm. So that credit assignment problem is essentially how we find these weights. Well, that's the problem of finding the weights for your network.
Yes, gradient descent is a very general technique, a super general concept from more than a century ago, which can be used to credit assign in complex systems like these recurrent neural networks, the individual components of the networks, which are the connections and the weights on these connections. So each of these connections has a little number on it, which says, how strongly does this neuron over here influence this neuron over here at the next time step? Mm-hmm. And the number is maybe 0.2 or minus 0.5 or minus 6.2. And it's contributing to the error at the output side, right, which was maybe observed 1,000 steps later. And now the question is, how can I trace back this influence? And how can I then change this connection such that it becomes a better connection, and that my entire network becomes a better network such that the error gets smaller? Mm-hmm. Yeah. And then the efficient way of computing these gradients through automatic differentiation, or backpropagation as it is called today, that was introduced in 1970 by Sepulveda Inma, but then he phrased that as a very general thing, and he didn't apply it to neural networks. That was then done by other people, in particular Paul Werbers, around 1982, when he really applied it to neural networks.
Okay.
And then in the 80s, computers became faster and faster. And by 1985, they were about 1,000 times faster than when Linda Inma wrote this down. And also many academic labs for the first time in the 80s started to have really computers to play around with. Mm-hmm. Desktop computers. Today everybody has that, or has it as a smartphone instead. But back then this was exciting new stuff. And then people started playing around, and for the first time with very small networks, they learned interesting behavior on certain little toy problems. Mm-hmm. Yeah.
Mm-hmm. But we couldn't move past toy problems because of this vanishing gradient issue, which Sup identified in his research paper, which led to the creation of LSTM networks. Tell us about LSTM and how the creation of those fell out of the findings.
Yeah. So the long short-term memory, as it is called, the LSTM, falls out of this findings because it basically overcomes the problem of vanishing gradients through a very, very simple trick. All we have to do is have a very stupid, simple unit, a particular type of neuron in there, which has the simplest activation function one can think of, which is the identity function. And then, if that neuron is connected to itself by a connection of 1.0, then at the next time step, it will basically replace what it had before as an activation number, for example, 0.7, by the same number, 0.7. Mm-hmm. So now you can imagine that if you run that for 1,000 time steps, then nothing happens for 1,000 time steps, and all the time 0.7 will be stored in this unit. Right. At the same time, as you are later propagating error signals back, because there was a difference between what the network should have done and what it really did, Then, if you know something about gradients, then you know that all the time as you are propagating errors backwards, you have to multiply by the derivative of the activation function, which is 1.0, because it's a very stupid activation function, which is just the identity function. And then you multiply by 1.0 again through these recurrent connection, which also has a weight of 1.0. And then, now it's obvious, certainly, as long as there are no external perturbations in little stupid networks like that, you can propagate errors back not only 5 steps or 10 steps, but hundreds and thousands and millions and billions of steps. It's not finished yet, because with that simple type of network, you have all the limitations that you get through linear systems, because the identity function is just a linear function, and there are many things you cannot learn by just linear functions.
Right.
Now, that's the reason why you have to surround the little tiny linear unit, the constant error carousel, as we call it. You have to surround it by a cloud of very non-linear units, which we call gates. And these gates then basically learn through exploitation of the error signals which are being propagated back in these simple guys in the center of these LSTM cells. They learn to adjust their own connections through gradient descent such that they open up at the right moment and let new stuff into these cells, into these memory cells, and they close down at other good moments such that the memory in there is protected for a while until they open up again and let it out such that it can influence the rest of the network. And so all of this is now being learned by these long short-term memory networks, the LSTM networks. And they are called long short-term memory networks because they are basically inspired by what the biologists know as the short-term memories of recent events circling around in form of circulating activations in your brain. But it's a short-term memory that lasts for a long time. And that's why it's a long short-term memory, because it can last not only for 5 or 6 or 10 steps like in the first original recurrent neural networks, but it can last forever, basically. Mm-hmm. So that's why it's a long short-term memory, an LSTM. Mm-hmm. Yeah. Now, you said that this was the solution to everything. However, it's not quite true, because we also had to wait for faster computers. Mm-hmm. Back then already, there was an old trend which held at least since 1941, when SUSE built the first program-controlled computer that really worked. Back then, SUSE could do roughly 1 operation per second. But since then, every 5 years, computing became roughly 10 times cheaper. Mm-hmm. And then by the time when NNaisense, for example, did his thing, that was 30 years later, computing was already 1 million times faster, but it wasn't good enough. Right. And then in the beginning of the 90s, that was another 20 years later, was roughly 10,000 times faster than during NNaisen's time. So it was roughly 10 billion times faster than during SUSE's time. Mm-hmm. Is that correct? 40 plus 90? Yeah, seems correct. But it was still not good enough to be commercially viable. Mm-hmm. But then by 2010, roughly, computers were cheap enough and the factor was high enough such that all the potential in the LSTM networks really could unfold itself. And I think since 2015, it's widely used in commercial applications, for example, for the speech recognition on 2 billion Android phones.
I'll maybe ask you to talk a little bit about the use cases, the applications of LSTMs that you find most interesting. But before we get to that, has the fundamental technology changed much between 1995 and 2015?
The fundamental insights were really from the previous millennium. Mm-hmm. One has to say that. However, there came a couple of really nice improvements around 2000. My second LSTM PhD student, whose name was Felix Geers, he was the first author on a paper which introduced something called the forget gate, which is a particular recurrent gate unit, which turns out to be really useful for many applications where the network has to also learn to forget sometimes stuff that it has observed in the past, to make room for new things, and to do that in a very controlled fashion. And so today the vanilla LSTM, as we call it, is a little bit different from the original LSTM. And there are a couple of topology evolutions that came in. For example, in 2009, Justin Bayer, another student of mine, was the first author of a paper which showed that you can evolve through artificial evolution LSTM-like architectures, which have the basic concepts of LSTM in there, but which sometimes change a connection here and have a different topology there and so on. That was in 2009, and there it was possible to show that in certain applications this type of LSTM topology works better and faster and learns a little bit faster than this type of LSTM architecture. So there has been a couple of improvements of this kind, although the basic fundamental ingredients, they date back to the previous millennium.
So this last thing you were describing, the evolutionary LSTMs, if that's the right way to describe it, the core insight there is basically you've got several different types of structures for LSTMs, and you can, based on the problem you're solving or the objectives, switch between them on the fly, or is it something else?
This is about the basic architecture of an LSTM-like network. And if you look at your own brain, for example, it's a product of evolution. And all these little special types of architectures that we find in your neurons, somehow they evolved over millions of years because some of them just work better and are better at learning certain things which are important for your survival than others. And so the same thing happened there in our artificial evolution of topologies, where you give the system the freedom to come up with new topologies which deviate from the original LSTM architecture a little bit, because we don't have a proof that a particular LSTM topology is optimal for all kinds of things.
Okay.
There is no proof like that. So we try to figure out, maybe we can automatically find the optimum topology in a problem-specific fashion, because maybe for this problem over here, you need a different topology is better than for this problem over here. And so we were able to show then that there are indeed applications where you can profit from this additional optimization of the topology through evolution.
Can you elaborate a little bit on the notion of topology? What makes a network fundamentally LSTM, and what are the things that can vary from one LSTM topology to another?
Yes. So the vanilla LSTM cell has 4 little neurons in there. There is the central neuron, which is the stupid one that I mentioned before, which has just the identity function as an activation function. Then it is surrounded by 3 gates, which are multiplicative. So there is this thing called the input gate, which is a normal standard neuron, a nonlinear standard neuron. And if that one is active, it can completely open the access to the central unit, the constant error carousel. Or if it is shut down, if it is 0, then nothing can flow into that central cell. And similar for the output gate. And then there is this recurrent gated unit, the forget gate, which basically can manipulate the self-connection of the stupid cell, of the cell with the linear activation function, to itself, and can make the cell forget stuff that was stored there for a while, and can learn to do that on. Now, you can come up with all kinds of variants of that topology. Maybe you have a little connection going out directly from the central cell to these gates. And these are called peephole connections. Okay. That's what Felix Geers also called them. My second LSTM student in 2001, roughly 2000, something like that. You can have additional modifications of the architecture. And sometimes it's useful. Because, as I said, there is no proof that a particular LSTM topology is optimal. Right. So you might want to use the principles of evolution to search for good topologies automatically and to take the existing one, which is pretty good for many applications. Vanilla LSTM is really good for many applications, but even further improve it. Mm-hmm. So that is the approach behind that.
Okay. You talked a little bit about this, but if we can take a step back, what was the kind of intuition for all of the, for the LSTM cell architecture, right? At the point that was developed, and correct me if I'm wrong here, I think of traditional RNNs as being just a lot flatter, whereas LSTMs have these cells that are doing all this funky stuff. Do you think about it that way?
Yeah. So it's true that the traditional recurrent networks are very straightforward. It's just a bunch of nodes with nonlinear activation functions, and everything is connected to everything. Yep. And at every time step, each of these little nodes is computing essentially the weighted sum of all the connected guys at the previous time step.
Super basic.
It's very simple and basic and beautiful also, because everything that's simple has a tendency to be beautiful.
An elegance
except
to it,
that it was not quite, it was a little bit too simple. So you need a little bit of additional structure to make sure that these memory effects hold. Now, the LSTM is more complicated, but it's also very simple because you can write it down in 5 lines of code. 5 lines of pseudocode are sufficient to explain it. So maybe a traditional recurrent network, you can write it down in 1 line of pseudocode, and this one needs 5 lines of pseudocode. Maybe something like that. And still, the principles are very simple because you have a very stupid, simple linear cell at the heart of each of these LSTM cells. And then you surround it by a cloud of nonlinear gates such that these gates can learn to open access or close access to these memories. And the network itself can learn to use these gates to put important stuff into short-term memory and ignore noise and so on. Yeah. Well, as Einstein said a long time ago, you should make things as simple as possible, but not simpler. Yeah.
Very good. To what degree does the LSTM, there are some related, I think, concepts that come up in deep learning, like attention and things like that. How does attention, for example, relate to LSTMs?
Yeah. So any recurrent neural network, of course, already has something like internal attention, because what it can do is essentially it can learn to direct internal spotlights of attention, if you will, to certain parts of the network. We can say, let's highlight this part of myself and let's ignore this part of myself. So in a way, the internal computation, which is based on the program that is implemented on the recurrent network in form of its weight matrix, this attention can be learned in a problem-dependent fashion. And so I think my first paper on that was in 1993, where basically a recurrent network learned to direct its internal foci of attentions. Is that the correct plural? The plural of focus?
I believe so, yeah.
Focus, is it foci? Okay. So the foci of attention, and then could use these highlighted internal patterns in Hebb-like fashion such that it could associate through something called fast weights, these internal attention highlighted patterns, such that it could do certain things that you cannot do with traditional networks, because it had these extra fast weights, which is actually a topic that has become really popular again very recently. So attention is something that was implicit in many recurrent networks already in the past, and now it is waking up in very interesting commercial applications again.
Speaking of commercial applications, we talked about a few of the commercial applications of LSTMs. Are there others that come to mind for you that exemplify its, power, flexibility, interest?
Yeah, so I think it's interesting to see that not only speech recognition, but also the next higher level, natural language processing, can be done by the same architecture. Right. So with speech, for example, every 10 milliseconds, a new vector of numbers, maybe 40 numbers or something, streaming into the system from the microphone. With language, it's quite different. There you already have letters and words and so on. And now on this higher level, which is basically derived from this elementary level of speech, you again can use LSTMs to, for example, understand text. For example, read some document and then try to make a short summary or classify that document. Maybe say the document is a CV of a person and you want to compare it to another document which is a job advertisement. And then you classify the document with respect to the job ad and you say, okay, this guy's a match or not. Machine translation, maybe the most visible application, is now what Google is doing since 2016. Since November 2016, Google Translate is not based on the old system anymore, but it has LSTM at its core, and it has become much better than it used to be. Mm-hmm. And especially the most important language pair in the world, which is English to Mandarin Chinese and back, mm-hmm. There the performance is much better. There was a time when the Chinese, they laughed at the translations, and they are not laughing any longer. So. And then the same thing can be used, for example, with slight modifications to segment images, which again seems like a totally different problem.
Right.
The same thing can be used to, well, that seems, again, closer to natural language processing, can be used to train chatbots. Mm-hmm. So you have lots of chats between A and B, and you then just train your LSTM to imitate B whenever it answers something to A. Mm-hmm. But maybe you have lots of A's and B's, and so it can learn from many, many different chats. And so it's suddenly even relevant for this old idea of an AI test, which is called the Turing test, which is about chatting with some other partner. And the question is he a human or is he a machine?
Right.
And so let's see where that is going to end at some point. Then the same LSTM also can be used for all kinds of other sequences, such as music composition. More and more people, again, interested in that. Doug Eck in my lab, about more than 10 years ago, was the first who applied LSTM to music composition, where the goal was to overcome the traditional neural music composition, which existed back then already, which was able to learn the basic harmonies. Mm-hmm. But then if you listen to compositions, they sounded like music, like stuff that in principle, for example, when you train it on certain pieces by Bach, which is a favorite of many of these neural network guys, then even in the 80s and 90s, it was possible by Mike Moser and Pete Todd and a couple of guys like that to learn the basic harmonies that you find in this type of music and then come up with randomized versions thereof, compositions of the network, so to speak, sure. Which sounded also like kind of this type of music, except there was no overarching structure. So more like elevator music versions of Bach or something. And then the goal was to also learn high-level structure that you find in many songs, like first there's section A, then there's another section A, then there comes B, then there comes A again, and then again B, something like that. Yeah, that was Doug Eck in the early 2000s.
And he was one of your students?
Yeah. He was.
And he's now at Google.
He is now at Google, yes, and he's running the, what is it called?
Magenta.
Magenta program.
I just interviewed him last week, actually.
Oh, yeah. He was a postdoc here, actually.
Oh, wow.
Yeah.
Okay.
And he was the first author on these LSTM for music papers. Yes, okay. 2003, I think.
Right.
Yes.
Wow. Great. So maybe as a way to pull the conversation back to your broader research around general artificial intelligence or artificial general intelligence, depending on your preference, you did an AMA on Reddit not too long ago. Actually, it was a couple of years ago, maybe.
Yeah.
And one of the questions that I thought was pretty interesting was, what are some beliefs that you hold that are controversial? In essence, that was the question. And one of those was that intelligence is actually simple, although we think of it as rather complex. Can you elaborate on that a little bit?
Yes, I think I can do that. So LSTM by itself is nice for pattern recognition and for doing really complex applications, but we should see that it's just a pattern recognizer. So the full AGI thing requires more. It requires reinforcement learning in an unknown, partially observable environment where there's no teacher who tells you what to do and where you have to maximize your future expected reward.
Right.
And so whoever can solve that problem in a general fashion has solved the grand problem of AI. And that's why almost all of our research of the past 30 years really focused on that. And so to us, the LSTM, which has now become popular, is just a side effect. It's just a byproduct of this more general work. You can use the LSTM to build a model of the world, to predict what's going to happen if you do that and that, but you still need another module which is learning, which is inventing new experiments and trying to figure out which sequences of actions lead to success and which don't. And that leads to this field of reinforcement learning with general purpose recurrent architectures, with recurrent networks, basically. Now, if you look at the LSTM, it's just 5 lines of pseudocode. So it's very simple. It's not the full true AI thing yet, because there you have to have the full loop through the environment. Act, perceive, maximize future reward or reward until the end of your lifetime. And for that, I sometimes speculate we need another 5 lines. And why am I so optimistic? Because we understand in many ways how to train the separate action module and how to combine that with a model of the world which can be used through the 5 lines of something like the LSTM, or something that is in the same ballpark at least.
Right.
And I'm further motivated to believe it's very simple because here in my lab, in the early 2000s, at least we already have found certain theoretically optimal general problem solvers, which are also very simple. So that many computer scientists actually don't, or machine learning scientists don't even know that, but there is an asymptotically optimal way of solving all kinds of computational problems. And this goes back to Markus Hutter in 2002 here in my lab. He was a senior researcher. Now he's a professor in Australia. And he wrote down a very simple method which solves any well-defined problem as fast as the unknown fastest meta program for solving that kind of problem, save for a constant factor, or say for an additive constant which does not depend on the size of the problem. So when you have, for example, a traveling salesman problem, which is about finding the shortest path through n cities where each city can be visited only once, then as the number of cities, n, grows, the problem becomes larger and larger, but it's still just a traveling salesman problem. Now, we do not know the best way of solving traveling salesman problems, but suppose we can solve it suppose there's an unknown method which solves it in n to the 17 steps. Then this method of Markus, the fastest and shortest algorithm for all well-defined problems, as it is called, will also solve it in n to the 17 steps, plus a constant number of steps, an overhead, which, however, is constant and does not depend on n. So as n grows, n to the 17 grows even much more crazily, and the constant overhead vanishes, which means that almost all problems are already solved in an optimal fashion, because almost all problems are large problems. There are just a few problems that are so small that the overhead still plays a role.
Just so I can make sure I understand what he did and what you're saying, is the idea that if a problem can be solved, that basically it can be transformed into some other kind of solution modulo a constant.
So what I'm saying is, you have a specification of a problem, and then you want to find a program that solves the problem. To approach that, you want to build a general problem solver, which finds that program automatically. Now, there is a general problem solver, which is this fastest and shortest way of solving all well-defined problems, by Markus Hutter, published in 2002 here in my lab, which essentially does that. And it's optimal however, only in an asymptotic sense. What does that mean? If your problem, for example, your traveling salesman problem with n cities can be solved in n to the 17 steps, then this super algorithm of Marcus is also going to solve it in n to the 17 steps, plus O of 1, as the computer scientists say. And O of 1 means there is a constant overhead associated with it. Now, the constant overhead is large, it turns out, because there's a proof search involved, and we hide all of the complexity of that in a constant, which can be done. No matter, even if the constant is large, then as n is getting larger and larger, as the size of the problem is getting larger and larger, the constant pales in comparison.
Sure.
And that's the reason why you already have, since the early millennium, an optimal way, a mathematically optimal way, asymptotically optimal way of solving all kinds of problems, especially the large problems, which are so large that we can ignore the overhead, the constant overhead.
Does this result just say that we can asymptotically solve them? It doesn't necessarily tell us how to do that.
No, it says it is a constructive method. It really tells us how to do that. Why are we not doing that all the time?
Exactly.
Why are we not doing that all the time? Because the small problems that we are looking at here on this planet in our daily lives, they are so small that the constant overhead does play a role. Yeah? And that's why we are still doing suboptimal things such as deep learning and LSTM and all kinds of things, you know. But at least from a mathematical perspective, we already know there is a mathematically optimal way of solving all kinds of problems in the fastest possible fashion. The fastest possible in a non-practical way, but at least in an asymptotically optimal way, we already have that. And it's very simple. It's a very short thing. So in that sense, you gain additional motivation to believe that in the end, the whole AI thing is going to be really simple. And in hindsight, we will look back and we'll say, we can't believe that it took so many thousands of years to understand and how to solve problems automatically.
So this tells you that by saying that if we can get far enough along with compute power, sophistication, and approaches to overcome this constant, then we're there. Like we can solve anything. Is that the idea?
Not quite, because what we really have to do is try to find a similarly simple thing for the small problems too. And one step in that direction is the so-called Gödel machine, which I published in 2003, which you can initialize with Marcus's algorithm, but also with other algorithms, and which essentially learns to rewrite itself in an optimal fashion once it has found a proof that the rewrite is going to improve its performance in a way that is not only asymptotically optimal, but generally optimal. So, however, also, this is not yet practical at the moment. However, getting out of that is that the very general problem solvers may be very simple and can be written down in a few lines of code. We still don't have the few lines of code that we need for a practical, general problem solver in this universe. But I think we are close, and the puzzle pieces are starting to fall in place. And I hope I will see it in my lifetime.
Awesome.
Maybe in the next few years.
Awesome. I've really enjoyed the opportunity to talk with you. I've certainly learned a lot. For folks that want to learn more about what you're up to, what's the best way for them to do so?
It's probably to look at my sprawling website, which contains more information than you ever wanted to see about us, but not only has the original papers, but also overview pages, which try to explain in rather simple terms what the experts might want to study in detail in the original papers.
Great. And we'll include a link to that in our show notes.
That will be so awesome.
Great. Well, thank you so much, Jürgen.
It was my pleasure, Sam.
Great.
All right, everyone, that's our show for today. Thanks so much for listening and for your continued feedback and support. For the notes for this episode, including links to Jurgen and the many resources mentioned in the show, head on over to TWiMLAI.com/talk/44. Please be sure to comment there with your feedback or questions. Also, please note, if you share your favorite quote with us via a comment or via Twitter, we'll send you one of our fab laptop stickers. I'll be in San Francisco September 18th through 20th for the Artificial Intelligence Conference, and I hope to see you there too. If you've already registered, send me a shout on Twitter and let me know. If you're still interested in coming but haven't registered yet, we've got a link and discount code on the show notes page, good for 20% off most conference packages. The following week, I'll be at Strange Loop, a great conference held each year right here in St. Louis. Strange Loop is a multidisciplinary conference that brings together the developers and thinkers building tomorrow's technology in fields such as emerging languages, alternative databases, concurrency, distributed systems, security, and the web. We'll link to the conference on the show notes page as well. Finally, another huge thanks to this show's sponsor, Cloudera. For more information on their data science workbench, or to schedule your demo and receive your drone, visit TWiMLAI.com/Cloudera. Thanks again for listening, and catch you next time.